Okay, so this is an exercise leading you to, of course, something that I want you to notice here, okay? Um, you see what this is. Now, there are a couple of ways of doing this. You can find U cross V and then multiply that by W, the dot product of W with that. But remember, U, when you say W cross U, W dot U cross V, what I was showing you here is that when you do U cross V, sorry, U dot V cross W, it is the same thing as taking the determinant of the 3 by 3 matrix where the first row is U, second row is V, and the third row is W. I hope you can see by calculating these two things that this is the same thing, right? So in order to do this, the triple scalar product, you don't really need to do U cross V first and then dot that with W. When you need to find W dot U cross V, okay, all you have to do is really to write W113 as the top row and then U cross V. So it's -1, 1, 2, 0, 1, 0, and take the determinant. All right, so this will be, remember, it's 1 times, and then the determinant of a 2 by 2 matrix. That's sort of like in the left bottom corner here, and that's 0 minus 2. Okay, minus 1 times, it's going to be 0 times 0. And then plus 3 times -1 times, -1, 1 minus 1, 0, which is -1. So this is -5, right? Okay. And then let's do the V dot W cross U. Now this, I mean, this sounds really strange, right? Because I'm not like switching the order. Well, I'm sort of switching the order, but you see what you're trying to find out. U dot V cross W turns out to be the same as W dot U cross V. How are we getting these things? And then finally, V dot W cross U. These all look like it's the very different things. But if you do V, that's 0, 1, 0 on the top, and then W, -1, 1, 2, and U, which is negative, that I wrote the wrong thing here, right? Because W is supposed to be 1, 1, 3. And then the last one is U, which is -1, 1, 2. And so when you do this, you will get, of course, oh, again, that's a bad thing, 0 times whatever, I don't really care, okay? And then minus 1 times 1, 2, minus -3. Did you see that? 1, 2, minus 3, -1. So that would be 2 minus -3. That's 5. And then plus 0 times whatever. Okay, so this is -5. And you notice here that it's all the same. Why are they all the same? Okay, so in the first case, U dot V cross W, that was the determinant of the 3 by 3 matrix, U, V, W, right? In the second case, what I did here was I switched the rows, so you have W first, and then U and V. Now notice here, what happened here is I took this W and put them in the front. Okay, so you put that on the top, and then these two just go down by 1. Right. So this is sort of a circular permutation. You take the bottom one, put it on top, and the second goes to third. First goes to second. You can do this again. Take this V and move it onto the top. So you have V, and then W goes down to the second place, and the U goes down to the third place. Sounds like watching the standings in baseball or something, right? So bottom goes to the top, everything else goes down by 1. And so the last one would represent V dot W cross U, right? So these are all equal to each other, and it's really not surprising, okay? Because what happens is when you change your rows this way, you're switching or you're interchanging two rows twice, okay? And in that operation, the determinant does not change, all right? So one fact, and this is a sort of interesting fact, is, and here's a fact, okay? U dot V cross W is equal to, now remember, W gets to the front, so W dot and then U and V will go to second and third places respectively. W dot U cross V, and then let's take the V to the front again, this time, V cross dot, and then W goes to the second place, U goes to the third place. So these are all equal to each other. They don't seem to be equal to each other, right? Because the cross product of the two vectors involved in the cross product is always different in each of them. But because of the way determinants work in matrix theory, these are the same. All right, now let's try to wrap this up. Oh, by the way, I should mention one more thing here. Another thing is the determinant has a certain property, okay, in matrix theory. And when you do this thing here called the triple scalar product, you will get a number, right? In this case, I had negative numbers, but the absolute value of that number, the scalar, in this case, would be positive 5, actually represents something, okay? Remember, the cross product was the area of the parallelogram. This time you have U, V, and W, okay? And if you have the U cross V, or in this case, or whatever, okay, V cross W, that would represent the area of the parallelogram. If you take the dot product of this, you get another dimension, and it turns out to be the volume of this three-dimensional version of the parallelogram. What am I talking about? All right, so when you have, well, let's say this is V and W, and this is U. The V cross W would be, the length of that is the area of the parallelogram. Now you take a dot U, or U dot with this, and then that's going to give you the volume of the three-dimensional solid where each face is a parallelogram. So one face is made by V and W, right? And when I say face, I mean the side. And then another one is U and V, and the last one is U and W, right? So so that's a six-sided figure. What do we call this thing? It's sort of like, you take a UPS box and then somebody just hits it over here and everything becomes a parallelogram. So it is called parallelopiped. Okay, it's actually not just a parallelepiped. It's the parallelepiped with U. Oh, sorry, this is supposed to be a V. Okay, U, V, and W as adjacent faces. Okay, so it turns out to be the volume of the parallelepiped. And again, the parallelepiped is what we call a six-sided or six-faced polyhedron in which each side is a parallelogram. Okay. All right, so let me wrap this up. In general, and these are some of the important observations, or maybe incredible observations, incredible meaning hard to imagine, right? But U dot U cross V. Now tell me, what do you think this is? U dot U cross V. Okay, this turns out to be 0. Now, why do you think this is? You have the two things in here, and there are, again, a couple of ways to think about this. But U cross V, one reason is since U cross V is perpendicular to U, right? So you have a vector that's perpendicular. So what happens when you take the dot product of U and the vector that's perpendicular to U? So that will be the dot product of two orthogonal vectors. Did you get that? If you take two orthogonal vectors and take the dot product, by definition, you get 0. So that's one reason to say that this is equal to 0, okay? Or since U, and V, well, okay, so maybe you can, what did I just do here? Okay. Hold on a second, something's gone wrong. I will fix that in just a second. Okay, maybe another reason you can think of is, remember u dot u cross v is equal to v dot u cross u, right? Because you take this to the beginning and everything else is moved aside or moved to the next thing here. And you know that u cross u is what? Is 0, okay? So that's 0. That's another way to think about that. And yet another way to think about this is the parallelopiped formed by u, and v would look like this. You know, maybe u is like that, and v is like that. But then the third component is u again, okay? So this is just a big, flat, parallelopiped. It's almost like you take that box and then just flatten it. What's the volume of something completely flat? The volume is 0, right? So that this triple scalar product has to be equal to 0. Yet another way to think about this is this triple product u dot u cross v is the determinant of u, and v. And again, if you have the 3 by 3 matrix or any n by n matrix where 2 rows are identical or even scalar product to each other, okay, this will just be 0. So there are many ways to think about this fact that u dot u cross v is equal to 0. Okay, so that wraps up this section 2.4. I should warn you, 2.5, lines and planes in R3. That's going to be a very long and maybe the longest section of chapter 3 or chapter 2. Again, it's completely free of calculus. We will not, and we haven't, and we will not be talking about any sort of a calculus concept in chapter 2. But just be aware, 2.5 will be a long section. And so that's something that you can look forward to because that means you will learn a lot of things in the next section. Okay, until then, now again, start doing your homework for section 2.4. And until I see you in 2.5, I hope you'll have a great day. See you then.